So yeah, with that, I'd like to introduce our first speaker, who's Yigit. He's a PhD student at the Institute of Neuroinformatics in Zurich at the minute. But from his website, I saw he'd done some really cool things beforehand as well. And today he's going to be talking about online training of spiking recurrent neural networks with phase change memory synapses. So over to you.
Yeah, thanks, Marcus, for the introduction. So today I'm going to talk about our neuromorphic approach to do online training of spiking recurrent neural networks using phase change memory synapses. Phase change memory is a type of memory device. It's a specific kind of memristive device that I will be explaining in the talk. So whatever I'm going to present here is done on simulation. But when we submitted this work, after a couple of months, we also collaborated with IBM Research in Zurich and tested everything on the hardware. And what I'm going to say here has already been tested on the hardware. They're the real devices, is the exact same settings. So you can expect these things to transfer from the simulation to the real hardware. Okay. So the goal in neuromorphic computing is to create efficient computing substrates for neural network type of computation. And we differentiate ourselves from the conventional accelerators, usually a conventional computing, in three different ways. One is that we are fighting with von Neumann bottleneck. So if you look for the energy consumption in the type of neural network computation, the majority of energy consumption goes to the data movements and data storage. It's not the computation itself. Computation is almost for free, but whenever you get your data from SRAM or DRAM, when you catch it, it's extremely costly. Actually, the percentage is usually like 95% energy goes to data movement and 5% is the computation. And the best way currently we know to attack this problem is using in-memory computing. So we localize the storage and also computation very close to each other and do the computation using the physics of the substrate. And we are using non-volatile memristive devices. These are small, non-volatile electrical devices that requires almost no static power consumption. So the circuit we usually use looks like this on the right. So each black shape here is a neuron, and it has, like, in this case, 5 synapses. Inputs are coming from here, from the other neurons. And whenever a spike, the voltage comes here, due to the Ohm's law, because of the conductance here in the synapse, it automatically transfers the current, and the current goes to here. So the same thing happens for every synapse, and the current sums up due to the Kirchhoff's current law. And you can have the vector matrix multiplication, MAC operation, or synaptic propagation almost instantaneously. So you apply electric pulses, and everything is basically multiplied with the conductance of this synapse, and current sums up. So everything is happening on the substrate. One cool thing about this circuitry is that if you apply the voltage pulses, the inputs from here, and sum it from here, you do matrix vector multiplication. But if you apply the voltage from here in this direction and sum it from here, what you get is the weight transpose, basically WT times X. And this is useful for the ANN applications. We also utilize the spiking communication. So when the sparse events data stream comes, we do asynchronous processing in analog hardware in an event-driven manner. So when there is no spike coming from sensory devices, we do not do any burn power. We do not burn any power. Everything is at the idle state. But of course, creating for this type of neural architectures, we are also looking for inspiration from neuroscience in both architecture level, also in the learning rule level. So instead of using like BPTT or directly backpropagation, we are looking for the local and online learning rules that depends on sometime pre-post, the third factor rules, like Hebbian type of learning rules. and also information encoding is inspired from neuroscience. So the goal in this work is to train a spiking recurrent neural network to do a motor task. But we would like to use in-memory computing fabric. So our hardware will be doing in-memory computation. But in order to do also the training, we have to do, we would like to have basically have a powerful online and local learning group. And the problem is that the analog hardware has limitations, right? It has the bit precision problem, it has the noise problem, and there are some nonlinear effects due to the non-idealities of the hardware. And for training, the problem is really unsolved currently because the credit assignment solution for spiking recurrent neural network is an unsolved challenge. But the idea here is that if we can have an algorithm that does this training with hardware non-idealities, maybe the training procedure itself will overcome these hardware limitations, and maybe we can have the system that does training and also copes with the hardware limitations. So I will going to talk about 3 building blocks that we think is really important for creating such a system. And I will start with the in-memory computing part with PCM synapses. In this part, I will be describing the hardware. Okay, so the substrate consists of the memory storage consists of the phase change material of PCM synapses. So this phase change material is basically 2-terminal non-voltage resistive material that holds a state. It means that, so these are very small, usually around 10 nanometer size devices with very small footprint. When we apply an electric pulse from one of these directions, the blue directions, we change the temperature distribution inside this active regime, which is called the storage layer, or germanium, antimony, tellurium. Really depends on the type of device you're using. And the way it works is actually very fantastic. So when you apply an electric pulse, you change the temperature distribution inside this device, very localized manner. Like in this case, like here, the red region, the temperature increases. And when it increases, it changes its phase from crystalline to amorphous. Okay? And when it changes its phase, it stays like that. It's permanently at that state. And by doing it, you can change the electrical conductance of the device, because there are 4 orders of magnitude difference between amorphous and crystalline regimes. Their electrical resistance is different. So if you apply a high pulse, you increase the amorphous region and device conductance increases. And if you apply smaller but longer pulses, you can reverse the effect and go back to here. So this is irreversibly, you can store information in these devices. But these devices are not ideal. So if you can look at these 3 plots, you can see the real measurements from 10,000 PCM devices. This is a actual statistical model from 10,000 PCM devices. So when we apply a single pulse to this device to increase its conductance, just like a log-term potentiation, right? You want to increase the conductance. The device conductance increase, but in a stochastic manner. This is called right noise. Because of the stochasticity in atomic configuration, you won't get the reliable increase, but overall, on average, it increases. But there is some nonlinearity in the device conductance increase. There's also read noise in these devices. So the real device conductance can be read by applying very small voltage pulses and looking at the current. But there's a small noise around the real conductance devices. So whenever you read the same device, you will end up getting slightly different conductances, although the real device conductance stays same. There's also additional problem with these devices, specifically phase change memory devices, which is called the drift problem. So when you program your device to some certain conductance level, which is G here, the conductance decreases with time. So this is called the drift problem. So if this is our substrate, and if you would like to see how the spiking recurrent neural network will act on this substrate, we are using these devices as a weights here. we would like to have the very good model of these devices. And here, this is the model that we are using. It captures the right read and the temporal conductance drift of these memristive devices. And this statistical model is built from getting measurements from 10,000 PCM devices. So what we are going to do is we are going to create a circuitry where each synapse consists of 2 of these devices. So you have 2 memristive devices. Whenever I want to increase the conductance of this synapse, I will send a single pulse to this device. So its conductance will increase. But this is just a positive number, right? It can be only positive. So, but I want to be able to represent the negative weights. So I'm violating many neuroscience rules here. And in this case, I will apply the pulses to other device, which is the negative device. And I will take the current difference between these 2 devices. So it can be positive or negative. So for every synapse, there are 2 PCM devices. Okay. Okay, the second building block is the credit assignment solution for spiking recurrent neural networks. What we want to do is we would like to solve the credit assignment problem using a credit assignment problem for spiking recurrent neural network. And this is the R architecture. So the architecture is very basic spiking recurrent neural network architecture. We have incoming spikes, incoming inputs X multiplied with the weight matrix, and this is the inputs layer. And there's also the recurrent layer, which consists of the spikes Z. And this recurrent layer is basically the diagonal is not connected, and it decays with some constant alpha. This is the membrane voltage of the recurrent, the layer neurons, and it has a reset mechanism as well. So whenever it spikes, and the spiking is determined with this Heaviside threshold function, the membrane voltage of recurrent layer decreases. For the output, we have just a leaky integrator output layer, which projects the spiking of recurrent network to an output layer with the output weight matrix, and it just accumulates in case it does not spike. So think of it as a motor unit. It just created patterns that might be useful for regression tasks. And here the task is really 1D pattern generation tasks for 1 second. So it consists of sum of 4 random sinusoids with random amplitudes and random phase. And this type of regression task is relevant for motor control and also reinforcement learning. So you can think of this system as a value prediction system. So every state you predict a value, and value is changing constantly. Okay, so this is the architecture, and this is the task. For the learning role, what we need is we would like to have a local, biologically plausible, and strong learning role, an online learning role. So strong learning role here means that there are many biologically plausible local learning roles based on just pre-post coincidences, some basic SCDP-like approaches. But here we want to have a learning role that can do credit assignment so well that it performs very well on the complicated tasks. And here we choose the eProp learning role from Guillaume Belec. So in eProp learning role, you have this architecture, and every time step you calculated the error based on the mean squared error based on your predictions and the target, and you project it back to the neurons. And each synapse has its own eligibility traces, local eligibility traces. So basically, BPTT is now factorized between local eligibility traces per synapse and external learning signal coming from the output layer. Okay, so you can do online learning with using the local information. Okay, so building block 3. So this is currently how the system looks like. We have the input neurons, we have input weight matrix, we have recurrent neurons that does this recurrent the processing with the recurrent weight matrix, and we have the output weight matrix and output units. Output units are not spiking. So the system generates the pattern, And we have a target pattern that we can calculate the loss. And eProbe gives us an estimation on the gradient. It does not calculate the BPTT gradient, it approximates it. And it gives us a delta W, the weight change that we would like to do in order to perform the gradient step. And from this, we can just update the weights in input, recurrent, and output layer. This is how we usually do simulations in 32-bit floating point system. This is how things work in normal the logic-based systems. But here the problem is that if you are using memristive devices, eProbe still can calculate us the delta W, the amount of weight change we should get, but representing it in the conductance is problematic because these devices, as I've shown, has non-idealities. It has this right noise. It has a bit resolution. So we have to find a way to implement the gradient step on this non-ideal hardware. So although we have very powerful learning rule, we have to still do this transformation. Okay, so yes, I just mentioned this. Due to these non-idealities in right model and the drift, this delta W calculated by eProbe is not directly implementable on the hardware. And here I will go through 4 different approaches we tried to solve this transformation. So if you have a gradient information calculated by a very strong learning rule, but you have an unideal substrate, what you can do is you can very simply look at the sign of the gradient. And depending on the sign, you can send a single up or down pulses to one of these 2 devices. So if you remember, for every synapse, we have 2 memristive devices, right? And depending on the sign of the gradient, we will send a single pulse, which is with fixed learning rule, if you want, to these synapses to increase their conductances. So the synaptic conductance will either increase with a fixed step or decrease it. But you don't want to do it for every time step because it's super costly. What you can do, you also set a stop learning regime. So if this the magnitude of the gradient is smaller than some fixed threshold, you don't do the update. You basically skip it. So if you really need the synapse needs an update, you send a single pulse. So it's very efficient to do it on hardware, right? It's very simple. You just send a single pulse to the device. The second approach is stochastic update. So in this case, you can map the gradient magnitude to an update probability. So instead of doing the sign-based or thresholding based programming, what you do is you just calculate the gradient with eProbe, and depending on the magnitude of the gradient per weight, you update it. You assign it to the update probability. The other thing you can do, although this is not efficient in terms of the scalability, for every synapse, you can have multiple memristive devices. So instead of 2, you can have n positive and n negative devices. And whenever you calculate the gradients, you can increase or decrease one of the n devices in a sequential order. So it will give you a wider range for doing updates. So your effective bit resolution will increase, and also the noise due to the upgrade will be scaled down because you are now summing the current over n different devices. The other approach is the mixed precision update. So this is also recent the methods that people developed. So what you do is you calculate the gradient information using eProbe on your circuit, but you don't do the update. You accumulate the gradients on a digital coprocessor. So you have a digital coprocessor next to your ideal neuromorphic substrate, that accumulates the gradient information until it matches the right resolution of these memristive devices. So it means that you accumulate, so your learning rate is actually now is much, you can implement very small learning rates because you accumulate the gradients a lot, and you can reflect this change on these devices, low bit resolution devices. Okay, so this is the performance comparison. So this is the pattern generation task, and with different targets, then the different recurrent network outputs. So if you look at the sign gradient, which is the first one here, its MSE loss is 0.2. So the MSE loss, whenever it's smaller than 0.1, in the paper we are showing it more precise, the y is 0.1. You can think that this task is solved. So if you apply sign gradient or stochastic update or multi-memristive device with n equals 4, n equals 8, you cannot solve the problem. You cannot. The problem is still too complex, and you cannot solve the non-idealities coming with the PCM cross pair. The only method that worked is accumulating gradient, this mixed precision approach. So really, if your substrate is memristive devices, currently the only way to do training is to accumulate the gradient in some core processor and doing the update whenever you can really reflect this change on the device. So we also wanted to compare this with a digital low bit precision hardware. So we run another set of simulations using the same approaches, but this time we don't have read noise, we don't have write noise, we don't have drift. We only have 4-bit resolution, the weights that are perfect, as like SRAM weights. You have 4-bit resolution weights. In this case, sign gradient, sending single passes almost worked. Stochastic update worked very well. Multi-memristive devices n equals 8. This corresponds to, if I remember correctly, like 7 bits of the different 7 bits of the weights. It worked. And mixed precision also performed the best. Okay. And when we look at when we have a closer look in the gradient accumulation, we show that, so one criticism usually you can get when you use memristive devices, that the programming of memristive devices is costly. So it burns a bit power when you want to program it, because you change the atomic structure of the device. Although it's not much power, still you would like to decrease the amount of programming pulses that you want to apply. But if you can accumulate the gradient in coprocessor, we show that a very small number of devices actually are programmed during the training. So it's only like 0.07% of the devices are programmed during the training. Of course, this is a problem-dependent statement. And one of the problems that usually you can get with this kind of differential configuration, so if you have two devices that represent the synapse, one is positive, one is negative conductance, kind of. If you increase one conductance and increase the other conductance, because this corresponds to the decreasing, this corresponds to the increasing the synaptic conductance. At some point, your weights will saturate. So you have to check regularly whether your device's conductance are saturated, then read it, calculate the effective conductance, and reprogram the device. But in this case, in this scenario, it's not needed. We checked it, and basically nothing has to be checked, because the number of pulses that we are applying already very small. And at the end, we achieved very sparse inference activity around 4 pulses. Okay, to conclude, we demonstrated an online training, spiking recurrent neural network with phase change memory synapses. We compared multiple weight update methods, and we showed that the best solution is accumulating the gradients until it is transferable to the bit resolution of these memristive devices. But if you have a quantized ideal memory, just stochastic update or 8-bit resolution also performs very well. The future work is comparing with this RTRL and OSTL, which are two different learning rules for spiking recurrent neural networks. And we are also now working on implementing eligibility traces per synapses. So if I can briefly explain the last work that we are doing, is that I've shown you the biggest problem, which is the drift problem of phase change material. So when you program a conductance, the conductance field decreases with time. This is the biggest problem of phase change memory devices in the industry. And the reason is that when you apply a pulse, any pulse, it creates some stress state on the device. And there are some experiments that shows this device then goes through a structural relaxation, which increases activation energy and intertrap distance. These are not important details. You don't have to know this, but it's just whenever you program this device, either set or reset, you create a stress. And this stress causes the resistivity increase with time. So this is a bug of the material. And here we are taking this material back and implement it use it to implement eligibility traces per synapse. So what we've done is we fabricated germanium and titanium materials, the materials that I've shown you, and do some measurements. This is the preliminary, the measurements we've done. We basically increase the device conductance by applying set pulses, then watch it decreasing. So with this mechanism, actually, you can have eligibility traces. You can implement eligibility traces per synapse in a scalable manner. And we show in this paper that our approach to implement eligibility trace, because implementing eligibility traces is a hard problem. It has to scale with the number of synapses. And if you want, you cannot use the capacitors because capacitors are really big. And this was one of the biggest bottlenecks to implement specific learning algorithms for spiking neural network hardware that requires eligibility traces. So depending on your learning role, you can just apply set pulses to this device, increase the conductance, and it will decay. So the next step will be using this eligibility trace with implementation using phase change materials, not as an eligibility trace and EPROP learning rules. Currently, we are using only to represent the weights, but we can also use the same material, but the material back to implement eligibility trace. Okay, so with this, I would like to thank my co-authors, Charlotte Frankel, Melika Payvant, and Giacomo Indiveri. The preprint is here. The real hardware measurements will be, I think, released soon with AICAS paper. And the simulator, including EPROP implementation, phase change memory model, and this crossbar array, these programming methodologies, that 4 different methodologies, are all available and open sourced here in GitHub. Yeah. So now I can take your questions.
Thanks very much. That was really interesting. I don't know if someone had, it's just over past, so does someone have a quick-ish question? And then we can have Kayson and come back at the end for more questions. I mean, okay, I'll go. I guess something I was kind of curious about was, so because the networks you were simulating had about 100 units or ish. So I was just wondering, like, when you're using the chips, like, how large are they physically? It's quite hard. It's just a bit hard to imagine the size of the chips, the actual devices.
Maybe 1 second. Maybe I can show you.
Sure.
So this is a board. Can you see?
Yeah.
So this is a board. This is a testing board for one of the devices, the memoir devices, which is not published yet. This is a testing board coming with FPGA, and this is the memristive. This is the neuromorphic chip. It's called memoir. So it's actually here.
Cool.
Very, very small, and it has 256 input, 256 recurrence, and 256 output units. It's actually pretty tiny. Although these are like prototype devices, they can be really tiny. We have larger, more general purpose neuromorphic chips at the Institute of Neuroinformatics that has 4,000 neurons, and you can stack these chips But again, these are prototype devices currently.
That's great.
Yeah.
I hope someone got some screenshots of that. So. Cool. Well, thanks, Yigit. I think now we'll move on to Kayson. So if you could stop sharing your screen, that'd be great. And Kayson, if you could share.
Yeah.
So yeah.
Quick question. How much noise do you have from my microphone? Will I open the window?
No noise at the minute. It sounds good at the minute.
Okay, so just maybe, why should I risk it? Whatever.
You can give it a quick test if you like.
Yeah, it's fine. I mean, worst case, I open it. It's better than the other way. Yeah.
So yeah, our next speaker is Kayson Fakhar, who's a PhD student at the Institute of Computational Neuroscience in Hamburg. And he's going to tell us about some work, which I found really exciting. Yeah, I remember when the first preprint came out, I was really excited about it. And yeah, did lots of journal clubs and discussion on it. So yeah, really interested to hear more about it and about the new paper, which is just put on archive, I think, as well.
Yeah, so thanks. Do you see my pointer, like the mouse itself, because it doesn't have a laser pointer, it's a PDF file.
Yeah, we can see the mouse.
Okay,
yep.
Okay, cool. So my work, I think, I mean, our work actually is a bit different. Doesn't spike. And the idea is that, well, the title is, if we have a framework that is a game theoretical framework for putting numbers on causation, which takes things into like a philosophical turn. So I'm going to start with that, actually. It's more fun. And the idea is that, so what do we mean by causes? What do we mean by causation? And we mean actually the most intuitive way you can think of as something causing something else. And then how can we kind of establish that relationship? By manipulating it, by intervening. And for example, if you're doing neuroscience, really by doing optogenetics, TMS, all those things. And this happened to actually have some authority over other methods in a way that it settles debates. For example, there are activations seen in some region, and then you really want to make sure that it is that region that is doing that thingy. So you go ahead and perturb it. And if it worked, and if it, like, let's say the behavior is also gone, then we have some causal link established. And yeah, there are problems with that. Otherwise, we wouldn't having this discussion here. And I'm going to show the problems we found, at least like 2 of them here, and then the solution that we figured out, well, I didn't figure out, but I'm working on, is the game theoretical framework. So the problem is illustrated here as one lamp and some switches. You can think of these as brain nodes, and this one as some sort of, I don't know, behavior, like decision-making, or I don't know, something you like. And so what do? We want to establish causation between these regions, I don't know, one or more, and this this behavior. So we switch them off. You know, we switched them off. This one, that didn't work. So next one, that nothing happened. This one, oh yeah, we have it, and we have this behavior also, lesion damage. Some kind of something went off. So now we have a causal role established from one node, from one brain region to this behavior, and it's kind of reproducible because you can flip it on, and behavior comes back on. So everything works the way we like it to work, unless someone accidentally turned the other one. So another random node is off while this one is off, and now the behavior is back on. So it's basically like we had one lesion, one deficit, now we have 2 lesions, no deficit. And that's why they call it a paradoxical lesion effect. It's first seen in '66. And then if you want to just catch up what's happening and the possible mechanisms, you can read this nice review. But it's all, I mean, it sounds like it should be all in the brain, but it's not. It's we found it in neural networks too. And the frightening thing for me was that the mechanism in neural networks is so simple that I just guarantee that if you have something interesting, you will have these paradoxical lesion effects too. If the system is interesting enough, it has it. So what's the implication? The implication here is even if we lesion all these nodes, we still can't really establish a causal role because there are interactions among the nodes naturally that we have to account for. That means that we have to lesion combinations of nodes, and well, we don't know where these interactions stop. So we have to systematically perturb or manipulate all combinations. That sounds scary, but it's possible. The other problematic thing that is an extension of what you see here is that that computation might be so distributed that the behavioral outcome of that lesion is not straightforward anymore. So you lesion all these combinations, even randomly, whatever, but it's not that clear cut. It's not on or off anymore. You see weird outcomes. For example, the light flickers. I don't know, it gets brighter, it gets dimmer. So you have to now assign causation to all of these, because by that classic definition, we manipulate the system, we manipulate each of these, and something happens at the end. So if manipulation is everything we need, then everything is doing everything, and we're back at square one because we didn't learn anything from. So put these two together, we should do something better. We should do better than just establishing causal relationships because of these two problems at least. And what's that? So first of all, we have to acknowledge the complexity, because the brain is a complex system. Definitely the causal structure there is a complex also. So we have to acknowledge that it's fine to have this distributed regime and everything doing everything. So if that's the case, then we should put numbers on them. So everything is doing everything, but how much? That's the intuitive question. How much they're causally contributing to something? And this is what the game theoretical framework does for us. It's already available for Python. You can read the documentations here. I can click, but I don't want to. But what I want you to do now in your mind is to replace Shapley value, which is someone's name, very, very cool guy, but with causal contribution. So wherever you see Shapley value, you just assume it's causal contribution. I didn't change it here because the toolbox name is MSA, so I couldn't just change it by myself. And let's get to the algorithm. Let's see how it works actually under the hood. You have a network. Let's say it's just 4 nodes. It does something. I don't know. It solves a task, whatever, working memory. And then you can redefine the scenario here as a game. This is the game in game theoretical way. So this is a game, and these are the players, A, B, C, and D. You can actually be creative with the players and do all sorts of different things, and that's fine. Very, very good, actually, do it. But what we do is first from this set of players here, we produce something called permutation space. And that's just an estimation method, because if you think about it, lesioning every combination of a large network is just impossible. So we sample things, but that's just for that part. Yeah, we get these, and then we just shuffle them in space, like different ordering. And from each of those permutations, we produce combination blocks. So we just expand that into this. So if you have B, C, A, D, that is basically A, B, C, D shuffled. The next one is BCA, the next one is BC, and the next one is B. This is our instruction of what should we do with the network now. If we have BCA, then it means we have to play the game once with only B, C, and A. So D is lesioned, okay? And then if we have BC, it means we have to play the game with only B and C. So A and D now are lesioned. So now we are accounting for all those complex interactions, because we are lesioning multiple sites at the same time. And then we do all these lesionings that can be actually computationally expensive. It depends on your network size. This can be like millions of lesions, so but they're unique. And then we have to bring them back. We have to know the contribution of each node to all of these combinations. And this is how it's done here. If you have these two combinations, basically, then you can easily compute the contribution of one node, let's say D, to this particular grouping. So B, C, and A, when node D added to this, it produces this much, game theory-wise. But you can think of it as we had the performance here when all of them were there, and we had the performance here when D wasn't there, so the difference should be brought in by D. And then we do the same thing for all of the nodes. So we now have a lot of samples for one node contributing to all these coalitions. And then we just average it. That's it. That's your causal contribution of each node to the metric, to the game you're playing. And it quantifies things. And this actually answers both of our problems. We are lesioning higher order combinations. So that's that. And from all these thousands of lesions, we have a value that is proportional to how important that node was. And if it's not important at all, if it didn't do anything, then the value is 0. If it was hindering the performance, so if you take it out, performance gets better, then it receives actually a negative value. And the best thing about it is that when you sum all of these, you end up with the outcome of the grand coalition. So in a way, we just decompose this performance score or whatever we had into the corresponding players. And this is a sanity check. So if this doesn't work, it means something was wrong. We did that in our recently published preprint on like a echo state network, basically. And you can read the details here. I'm just going to go through some of the results. And well, let's go this way. We looped through all the nodes of this echo state network. It's a bio-inspired echo state network because the connectivity is small word connectivity, basically. And the task it's supposed to solve is that it receives some input signal. It's a chaotic time series, and then it should behave, it should produce in future time steps of that time signal, of that signal, basically. And then if you don't know about echo states, it's just basically a recurrent neural network in which we don't train these weights, the internal weights, and we just train like a readout mechanism that reads these and then produce this. So that's good because we actually want these weights to be fixed. We didn't want to touch them. So what we did here was to loop, to iterate through each node, call one the target, and then check what's happening, like what's the causal contribution, what's the causal influence of each node to this target, okay? And then we do MSA basically with all these minus this, and then track the change into this, the energy of this signal. So energy is L2 norm, basically. So if it has a high energy, then the L2 norm is high. If it has a low energy, like the flat signal, the energy is low. So we track that, and then basically we want to know the causal contribution of each node to the energy of the target signal. And this gives us a very nice interpretation of what's happening here. Because if you have a structural link here, and then you also have a causal connection here, causal influence, let's say, this is a direct influence. It probably used this structural link, but then there are indirect influences. For example, we lesion this node and the activity of this node kind of changed by some degree, and then that was an indirect influence because it must have passed via to basically intermediate nodes. So we can distinguish those, and that's good. And then we can read the resulting connectivity matrix, because if we loop through all of these, we will have an effective connectivity in a way. We can read it in two different ways. One is that the column-wise, like who's influenced by one node, and the other one is row-wise, and this means basically the same thing we were doing, we were talking about, like decomposing the influence of one node, like who's influencing this node. And this is the result, basically. So we have the causal influences here, and then this is the connectome again, just for you to remember. And wherever we have one value here and one value here, then it's a direct influence. So this is basically masked, causal influence masked by connectome gives you the direct influence. And then the other way around is the indirect influence. You can see immediately two things, I think, at least one thing. That is that the direct influences are mostly blue. So in terms of Shapley value, it actually means that removing them increased neighboring nodes' energy. That means it, in a way, it destabilizes its connected nodes. But then the effect of this destabilization was like a lower activity in distant nodes. The other thing that you can see with little help here is these strips, these vertical strips, that if you remember, it means actually there were some nodes here that regardless of the distance, they were influencing all other nodes the same way, in a way. So they just did their thing, and they're key players. And then the other thing we can do with the same data set is now we have the connectivity. I mean, that's perfect for neuroscience. We want to know the connectivity at its best precision, but now we have it. And we want, basically what's happening here is that this, for example, value defines the influence, should at least define the influence of that node over this node. But we also have the actual influence, and are they the same? Well, basically I have good and bad news. The good news is that there is like a trend. So the larger the structural weight, in a way, the causal influence fans out. So it's good in a way that there, at least it intuitively makes sense. But the other problem is that we have a lot of large weights that are not contributing to the other nodes at all. So there was, for example, some very nice, let's say, connection there that didn't do anything. So it's not that clear cut. It's not that easy to interpret. And here, for example, we had this misconfigured ESN with diminished dynamics, in which you can see there is just flat. So nothing is doing nothing, basically. That was just a control. I'm not sure how much time do we have, but I have this sum up here, but I have a lot of more slides there, so we can discuss them if we have more time. Otherwise, this is the take-home message. So we need to quantify the contributions and in complex systems. And this game theoretical framework does that. That's good. And then with these two, we now know that the knowledge of network structure, because of what's happening here, is probably not enough. We need more. So what that additional thing is, it's probably the dynamics and what's happening on that scale, but we don't know. And what we can derive from all this is that well, this is complicated, but things can only be worse in real brains. So I don't know, maybe we should think about what we are doing and how we can interpret the causal claims we have over the real brains. That's something that I leave it for you. And I also acknowledge the people that helped me a lot, and we work together to figure these things out. And yeah, if you want, this is my Twitter handle. We can stay in touch and, I don't know, discuss things further. Yeah, I think I will leave it here. But yeah, as I said, there are more if you want. Yeah. Oh, I did it in 20 minutes, I guess. Cool.
Thanks, Kayson. That was great. It was really interested and really nicely presented. So yeah, I'm happy to open the floor to any questions. But maybe I'll go first. So yeah, I guess something I was wondering is, so you showed at the end that the Shapley value, yeah, exactly this, actually, sorry.
This, okay. Yeah, sorry, I don't have numbers.
No, sorry, actually, the last slide.
This, yeah, okay.
This. Yeah, so you showed that the causal influence doesn't correlate so well with the structure weights. So I was wondering if you'd thought about like either essentially what would correlate well with the causal influence, or could you think of like a way of developing a method that would allow you to find those most important nodes from, like, for example, recordings of spikes or something like that?
Not from the spikes and recordings, but we actually, you're kind of asking the question of that I'm going to present the poster for in Fence. But we actually found something that estimates these causal influences without any computation, and that's the communicability of that network. So I don't know if you know, like, the communicability is just basically the efficiency of communication between every pair, given all the paths that they can kind of communicate with each other with. And it turned out the correlation here is much better there. And the reason is that if we don't have any interesting dynamics, just by like assuming the structure is everything, what you should get from causal influence is the communicability, because the farther you go, the less influence you will have over that distant node. So yes, if you want to just have an idea of what you should expect from a system in which you have some connectome for it somehow, like structural MRI or anything, you can just run the communicability. It's exponent of this connectivity matrix if it's binary. Anyway, you can run that, and that gives you, okay, I had it there. Here. That gives you some estimation, like something that is quite close, but not yet there. So this you can just ignore everything that's happening on this side. The causal influence here is quite like different. but I would say it's just because of the models I choose. So for example, the communicability here is both ways. So each node can contribute to the other node. But since I'm having this input signal to just one node is causally contributing to everything else. That's why this exists. But yes, here you can see actually the causal influence is pretty close to its communicability at the end. And this is the difference. I'm not gonna exploit, what is that, spoil more. I kind of did, but yeah, not more. Communicability is the thing you want, maybe, for now at least, yeah.
Communicability is all you need. We can keep an eye out for the paper.
Yeah.
No, that's cool. That's a good answer, though. Yeah, Venkat, you've raised your hand.
Right. Thanks, Marcus, and thanks, Kayson, for the wonderful
Hi.
talk. I just had a question about the structural weights versus the your metric plot that you were showing. Maybe I missed it, but why would you like the structural weights to correlate highly with causal influence? For example, there could be presumably nodes, unless I misunderstood what you were saying, nodes which have a low structural weight, yet they sort of have the ability to control the outcome in a way that suggests a high causal ability, whatever that means. So is that right, or am I completely misunderstanding?
Yeah, no, that's right. But if you think of it as like the way you actually formulate it, like the equation, this is W, and the higher the W, then the influence of that node over another node, not the output, over another node is multiplied. Whatever comes out from this node is multiplied by that W and reaches the other node. So the higher that, the higher the influence. Kind of assuming, yeah, that's true. I'm assuming that.
But the issue would be the non-linearities in between, right? So which don't necessarily make that argument as clean. Right?
Yeah, that's true. Yeah, that's probably the reason here, that you don't see the really linear, clear line. And yeah, that makes more sense than what I said about it should be the dynamics, because now at least we have concrete. It's the non-linearity of the thing in between.
All right.
But
okay.
yeah,
I had one more question with the indulgence of Marcus, if that's okay.
Yeah, sure.
Right. So, so sort of more broadly, and sort of this goes to your first point on the last slide, which is that we would like to sort of quantify causal contributions, right? And when you say it's necessary. So, sort of in a contrarian spirit, why do you think that's necessary? In other words, is this the means to some end? So one answer could be that, therapeutically you'd like to, help people and so on. But with regard to, let's say, things such as understanding. So it sounds like, if you didn't have these, the combinatorial barriers that you do, that the end game of this would be to have a really large truth table, right? Which tells you, which combinations, cause the light bulb to be on versus off. Right? But does that, what do we learn at the end of it? In other words, again,
No, I got it.
But I was just curious about your thinking on this.
Yeah, no, I got it because I thought about it before, actually. It's a very expensive thing to get something that you actually need to ask them, did it worth it? Yeah, this is what you're asking for. Yeah, so I would say, first of all, the good things are here. Here. So at least the number you get accounts for the things that you might have missed by just normal lesioning or by normal causal, like, I don't know, manipulation. So that's something that in a way it's better. And then you have a ranking at the end. That's true. So you have, instead of having something that is either causally linked or not, you have a ranking there, how much it's linked. With that, then that's just the beginning. So the paper we wrote on paradoxical lesions argues that the systematic perturbation of neural networks, that we start with this and kind of contrast the two regimes of lesioning. And then we figure out, okay, this one gives us some more information that was completely missing from the other one. And then from there, we have to just dig in, like figure out now what to do with that. So this by itself will just give you a ranking. And what you do with this ranking is really up to you. You know, you can actually say, okay, I'm going to just put like a threshold there. Whatever is above that, it's critical. Whatever is below that doesn't matter. Or clinically speaking, these hindering ones, or even machine learning speaking, these, why am I losing things? Okay. Oh yeah, it was here. That's why. These hindering ones, you can remove them. You can remove them and have better performance. You know, why you don't want that? That's cool. So I would say if you want to do this expensive thing, really depends on how much you care about learning what's happening inside that system. Okay, if you just want to see, okay, superficially some things are causal, then you can actually go ahead and do the normal causal analysis and just distinguish between if something is causal or not. But then if you really want to understand it, this is the first step. This is not the end. This is just how it starts. And what you do next is really up to you. And yeah, then we also did the same. So we started with this in our paper, and then we figured out, oh, the mechanism producing this paradoxical lesion is just so simple, so bad actually. Yeah. So
but
this is
but
how
also
it starts.
this point number one on assigning 0. So that's a sort of an average value, right? So it's possible that. All right.
Yeah,
So
in
I mean,
some
there are
combination.
Yeah.
But it means on average, it didn't really do anything. Either it was there or not. So it's
on average across interventions.
Across all the combinations, yeah. But if you can somehow exhaustively lesion everything, in this case there are like 2 to the power, 2 to the power of 4, then it's not like really, you know, uninformative anymore. So this 2, oh, actually I have some example. I didn't really think I have time here. Here's the ranking, for example. So I did the same thing for the behavior, like classic, you know, who's contributing to the energy of the outcome, you know. And then here's the ranking. This is what you were looking for. And then when we remove this one, it destabilizes the network. Okay. And when we remove this one, the energy is lower. So not that much, not as pronounced as this one, because it's on average. You know, yeah, that's true. And yeah, that's it. So we ended up actually correlating these 2 metrics and seeing that what's happening, what the node is doing inside the system versus what it's doing to the outcome. It's basically roughly the same thing. And yeah, so whatever you do next is just starts from here, this list, basically. That I think it's better than having uncertain, either it's causal or not, probably all of them are list. Yeah.
All right, thank you. A nice talk.
Thanks.
Just to follow up on that, there's a question in the chat from Jeremy Forrest, which I'll read out. So what general guidelines would you give to interpreting perturbation experiments using optogenetics or TMS or similar techniques? How do you interpret and better design those experiments given this tremendous complexity?
Yeah, that's reviewer number 2 asked the same thing, and it puzzled me for 2 weeks. Really, I was thinking, I really can't. I'm not in the position of giving any guidelines. So first of all, but I would say you need to just assume whatever, like not as an authoritative, like concluding result, but whatever you have there is just another result that needs to be verified in many different ways with many different techniques. If you just do something with optogenetics, your finding is maybe not necessarily better than whatever you did with some other techniques, just because correlation is not causation. This give biases our understanding, like biases are preference towards causation in this way. But my ideal scenario is that we actually do this multi-site perturbations, not that exhaustively, but at least maybe do some pairs, you know, on in real brains. I still don't know if it's possible. I don't think it is, at least for TMS. I heard there are some developments, but not in optogenetics. I think it's much better, but the problem is that people, I don't know, I haven't heard anyone doing this, like doing single cell lesioning and then expecting that each neuron has some meaningful result, like some contribution to the behavior. But yes, to conclude this part, I would say you just have to keep digging. It doesn't mean that you learn anything, basically. Yeah, it needs more. I think this is about this part I was looking for. Yeah, we might be somewhere here. We don't know.